I'll start with the general idea of this of these three sessions, and then I'll specify what I'm going to cover in the first one. So essentially the idea is that we have on one side the statistical mechanical models, a class of statistical mechanical models. So, and on the other side, imagine we have, the family of all kind of possible PDEs, but we will concentrate on the class of PDEs that are integrable. And I will specify what integrable means. So the idea of these lectures is to show several relevant examples where we can identify the partition function of a statistical mechanical models, where we talk about equilibrium, essentially equilibrium thermodynamics, so statistical mechanics for a large number of elements, and prove that the partition function satisfies some certain hierarchies of partial differential equations. So certain partial differential equations. For all the examples I will consider, these partial differential equations are completely integrable in some sense. So we'll see, depending on the system, we'll have to specify different notion of integrability. But we can, in those cases where you can prove that the partition function satisfies this hierarchy of partial differential equations, then here you can split, if you look into this ensemble of the set of partial differential equations, you can look at problems of classifications and in particular integrability, as I mentioned, and look at, for example, at the multi-scale asymptotics. So, and many other aspects. So, if this means that for each of these items, you can look at back what is the interpretation in the context of statistical mechanics, in the context of the properties of the observables. So, in a sense, you can, for example, use the classification of partial differential equations. For example, we talk about dispersive or viscous equations, and then look back into the statistical mechanical realm and try to understand what it means when a PDE is dispersive or viscous or dissipative in terms of the statistical mechanical properties. And in particular, the integrability will have an interpretation. What this means that is the PDE to which the partition function satisfies is integrable. What does it mean in that context? We will see that it means that the physical observables satisfy an infinite number of closure relations. And then, as you are interested, when you talk about statistical mechanics, what happens in the asymptotic limit where the system is very large? This means that you look at the corresponding PDEs, you look at specific multi-scale asymptotics, and you can identify different regimes that characterize the behavior of the statistical mechanical system in that limit. So, in order to keep things, concrete and practical, I will consider an example, and this example is the mean field Potts model. So, which incorporates for example, the mean field Ising model as a particular case, but also like a slightly larger class. So we consider in this example, we will see how to derive in a simple way some integrable differential identity for the partition function, and then extract equations of state of the model as a particular solution to this system of partial differential equations. So let's start with the definition, model. So what is the mean field Potts model? So when you do statistical mechanics, you need to equilibrium statistical mechanics, you need to define a Hamiltonian, okay, it corresponds to the energy potential. So I will write the Hamiltonian Hn, where n is the size of the system, minus j over 2n, the sum over I and j running from 1 to n, delta sigma I, sigma j, minus the sum over k running from 1 to q minus 1, hk, the sum over sigma i's to the power k, where I runs through 1 to n. Okay? Just to clarify the notation, what are we talking about? So, okay, delta of sigma I, sigma j is just the Kronecker delta, so it is equal to 1 when sigma I is equal to sigma j, in zero otherwise. Okay, so this Hamiltonian describes a particular interaction of a system of n spins, okay, sitting in a fully connected complete graph. Okay, so we have the spins sigma 1, sigma 2, so this is sigma I, and the spin sigma I can take any value out of q possible values. So A could be any of these A1 to AQ. Okay, so this defines the Potts model. And all interactions, so this graph contains the sigma i's are at the vertices of this graph. Now, I'm not drawing all of them, but in this graph you have all possible edges activated. And the weight of each of the edges is the coupling constant J. Okay, so J, capital J is the coupling constant, and it is the same for all possible pairs. It does not depend on the distance. If this was like the standard Ising model, for example, you would always have an edge between two nearest neighbors. But in the mean field version means that we consider a coupling constant J that is the same for all possible pairs. Okay, so this is the definition of the mean field model, which is different from the mean field approximation, where essentially you replace the original Hamiltonian with a Hamiltonian where each spin interacts with the average field. Okay, that's the mean field approximation. So this is the exact Hamiltonian where you assume that all possible interactions are possible. And also here, this is not like the standard Potts model, because I introduced this external interaction, which is slightly generalized compared with the usual one. So we got an external field, a family of external fields, HK, and we see that the external field couples with the individual spins in the standard way. So H1 multiplied sigma I, but also it couples with the moments of the spins, the powers. So I've got a different field, H2, which will couple with sigma I squared, and then H3 that couples with sigma I cubed, and so on, up to a power k minus 1. Okay, so the number of H I consider here is not random, so there's a particular reason why I need to consider k minus 1 external fields, and we will see this. At the end. Okay, so I hope I defined everything. Is the notation. So n is the number of spins. Okay, the number of spins. Okay, so There are different versions of the Potts model. Here, essentially, we provide a contribution 1 when a pair is aligned, and 0 in all other cases. Okay, so we get a contribution only if two spins attain the same specific value. So if we want to do statistical mechanics, we got the Hamiltonian, and then we have to define a partition function, a distribution of probability. So the partition function Zn will be a function of J and all the H, and this is standardly defined probably just as the sum over all possible configurations of the exponential of minus beta Hn, where beta is usually interpreted as the inverse of the temperature. Okay, so this is the Gibbs distribution, the standard Gibbs distribution, and the partition function is calculates this contribution over all possible configurations of the spins. So now the key. This example, just to provide the reference, was we discussed this example in a paper actually in collaboration with Paolo Lorenzoni on Physical Review E, and I'll just put the reference here just in case. So a few years ago. So this example contains several other examples, and I think a simple, quite nice way to illustrate the logic that tomorrow I will apply to the case of random matrix ensembles. So let's so the key point is in order to derive in this example a meaningful differential relation. So the key observation is to introduce a polynomial representation for the Kronecker delta. Okay. So I will write the Kronecker delta as the sum over L running from 1 to Q of the product over all K different from L of sigma I minus AK divided by AL times minus AK times sigma J minus AK divided by AL minus AK. Okay? So this is a quite nice trick, because we will see in a moment that this polynomial representation allows us to use the algebraic form of a suitable algebraic expression for the Hamiltonian to extract a differential identity. So in this expression here, so you can check directly that every time in this sum, every time sigma I and sigma j are different from each other, one of the two in the product will be 0, and then you get contribution 0, and then you can get contribution 1 only in the case sigma I and sigma j are equal to each other and equal to a particular value of A. So let's look at the particular example. Okay, so the case Q equal to 2. So Q equal to 2, and for an obvious reason, I choose also A1, the A1 and A2 to be equal to minus 1 and 1. So this connects to the Ising, so minus 1 and plus 1. So this connects to the Ising model. Okay, I choose, just for convenience, these particular values of A. And then if we calculate the delta, in this case, delta sigma I, sigma j, now, okay, just a simple algebra, just write the result. Sigma I, sigma j, plus 1 divided divided by 2. Okay, so if they are different, we get 0, and if they are the same, you get contribution. We get the contribution 1. So this means that the Hamiltonian, in this case, the Hamiltonian reads as minus j divided by 2n, the sum over I, all possible I and j of sigma I, sigma j plus 1 divided by 2 minus h1 sigma I. Okay, which is exactly, apart from, you know, a shift in the Hamiltonian, it's this is exactly the mean field Hamiltonian for the easy model. Okay, this is the simplest possible example. Okay, that is solved essentially trivially using usual standard combinatorial. But what I want to use this as a way to illustrate the approach. So in the Hamiltonian, just let me isolate the additional shift. Just a comment. So J is the coupling constant between the two, and H1 is interpreted as the usual, a constant external magnetic field that coupled with every single spin in the same way. So if we write the Hamiltonian this way, minus J divided by 4 times n, the sum over I and j running from 1 to n, sigma I, sigma j, minus h1, the sum of sigma I minus jn divided by 4. I just like to take this additional constant term away. And then if we introduce the quantity mu, which is the arithmetic mean of the sigmas, the arithmetic mean of the sigma, this is the magnetization. So what do we can write hn right away as minus j divided by 4 times n times mu squared minus hn h1. So there is n squared, h1 times n times mu minus jn divided by 4. Okay, so, and then the partition function, so of course, yes. Sorry? Oh, yes, so it's the, yeah, I said it, but I didn't write it, thanks, yes. So this gives us mu squared times n squared, and then we see that hn is just a quadratic expression in the magnetization, and then the partition function, it reads as the sum over all possible configurations. See the exponential of n times beta j divided by 4 mu squared plus beta h1 times mu plus beta j divided by 4. And then now we want to make a connection with the PDEs. I will define t, the variable t, as beta j divided by 4, and x as beta times h. Okay, so now it becomes quite obvious what we get. So hn is the sum over all possible configuration of the exponential of minus nt mu squared plus x mu and plus t Okay, so I substituted. So x mu, for some reason I write it twice, yeah, x mu plus t. And now the simple exercise is to differentiate. And we realize that if we differentiate the partition function with respect to the partition function, so yeah, this is, sorry guys, this is Zn, the sum over the configuration, okay? So now if we differentiate the partition function with respect to t, we immediately, we can immediately verify that this is equal to 1 over n, the second derivative of Zn with respect to x, plus n squared times Zn. Okay, so when you differentiate this with respect to t, essentially we get a factor of mu squared up to the product by n. And then in order to compensate this factor mu squared, we differentiate twice with respect to x. We drag a mu squared down, and then there is a shift when you differentiate with t, which is compensated by this term. Okay, so by direct substitution, you can verify that this is not a squared, right? So it's just n times n. So the partition function satisfies identically this equation, which is essentially the heat equation up to a simple transformation, up to an exponential transformation. Okay, so what we find is that in this case, for q equal to 2, the partition function for the mean field Potts model, so in this case it's called the Q-revised model for this particular, with this particular assumption. So the Q-revised model, for the Q-revised model, the partition function satisfies the heat equation up to a transformation. So essentially we can, instead of looking at the problem from the combinatorial point of view, we can say, we can find the partition function exactly as a solution to the heat equation. So the question is which solution we select for the heat equation. This is fixed by an initial condition. Okay, what is the initial condition? In order to select uniquely this solution, we can calculate the initial condition. But what is the initial condition? We can calculate it directly from here, which is the sum over all possible Cn, the exponential of minus n times x times mu. Okay, so this is the sum over all possible configuration, but this initial condition corresponds to the calculation of a partition function which is simpler than the original one, because instead of being quadratic, it's just linear, and this can be done straight away. So this is the sum over all possible configuration of minus n minus. So if I go back to the definition, this is minus x, the sum over from I to n of sigma I, and then we can do apply the usual trick. So we got the configuration of n spins. We single out, say, the last one, the nth spin, and we calculate this as the configuration, the sum over the configuration of n minus 1 spins, the exponential of minus x, the sum of sigma I, and this multiplies the two possible configurations of the last spin. So 1 and minus 1. So exponential of x plus exponential of minus x. So the sum is minus x, from 1 to n minus 1. Yes, that's right. And then we iterate n times, and then we get the exponential of x plus exponential minus x to the power n, which is the usual, so the partition function of what is the analog of the Erdős-Rényi model. So this is the initial condition that specifies the solution to the heat equation, which gives us the answer to the original question. Okay, so essentially, the heat equation is completely integrable in the sense that it's completely solvable. We have a formula. You can use the Poisson formula to represent the solution for a finite n, and then we're left with the problem of studying what happens when n tends to infinity, when the number of particles tends to infinity, the number of spins tends to infinity. So in this case, so to be fair, I mentioned the unique solution. Of course, there are some conditions in relation for the uniqueness of the solution to the heat equation. So I'm referring, Tikhonov proved that there is, the solution is unique, provided the initial condition doesn't grow more than exponentially. There is a specific constant, growth rate, but in this case, the growth is exponential, so we fall in the Tikhonov class, and this specifies the uniqueness. The statement is accurate. Okay, it's just to be a bit more precise on this. So I just want to write the initial condition in a more tidy form. So the comment I want to make at this point is that if we take the limit where n tends to infinity, clearly working with this equation in this initial condition is a problem, because for n, when n tends to infinity, the partition function, of course, blows up in the limit where n tends to infinity, and also the equation itself is singular, and then we need to work within the proper variables. We need to look at the proper observable or variables, rescaled variables, to study the thermodynamic limit where n tends to infinity. So, in particular, of course, we know the right observable is the free energy. I define the free energy with a plus sign, although the physical free energy is this is the Helmholtz free energy. Okay, so the state of the system will, in this case, correspond to the maximum rather than the minimum. But so we just bear in mind that minus F is the physical free energy, and in particular, this is definitely the object we need to look at in order to study consistently the thermodynamic limit. Before I do that, I just want to observe that, of course, given the partition function induces a probability distribution, and we can calculate the expectation values of any observables. For example, the expectation value of mu is defined as the sum over the configurations of mu, the exponential of I just need to write it, of t mu squared plus x mu plus t divided by the partition function. Okay, but a simple differentiation exercise will tell us that this is equal to, this is the expectation value of mu is equal to the derivative of Fn with respect of the partition function with respect to x. Okay, so we can calculate, and then I will use the notation. I will use the standard notation for the expectation value, so the expectation value of mu. Okay, so the expectation value of mu can be calculated explicitly once you know the solution. If you know z, you calculate f, and then you can calculate the expectation value of mu, of the magnetization, as the derivative of f with respect to x. And then I will use the notation m for the magnetization, for the expectation value of the magnetization. So to be precise, since I'm working at this stage at finite n, I will use the index, the subscript n. All right, so so now it makes sense then to look at what the equation for z becomes if you use the partition function. So Zn is the exponential of n times Fn, and then if we substitute, we get this equation dFn by d by dt equal to the derivative of Fn by x squared plus 1 over n, the derivative of Fn with respect to z squared plus 1, and then also the initial condition looks particularly nice. So this is the log of 2 times the hyperbolic cosine of x. So, but since the derivative of f with respect to x gives us the magnetization, I can derive an equation for Mn by differentiating here, left hand side and right hand side with respect to x. Okay, and this is what I'm gonna do. So the derivative of Mn, yeah. So Fn, so is so it's 1 over n. So the log of z, the log of this. The meaning of the rescaling. Yeah, actually, I'm observing this is the way the free energy is standardly defined, and I'm observing that with this definition, the free energy, and if I didn't know the result, I would have said, okay, how do I remove the dependence of n on the initial condition? Actually, in other cases, this is how you do it, because if you don't know the result, you need to devise the right variable that does the job. And because we don't know, for example, in random matrices, in some examples, we don't know what is the correct asymptotic behavior. So here we know it, and we just do a consistency check. So, and so then we write down the equation for the magnetization, and this is equal, the derivative with respect to t is 2mn, the derivative of mn with respect to x, plus 1 over n, the second derivative of the magnetization with respect to x. And the initial condition is the hyperbolic tangent of x. Okay, so this tells us that for the mean field Ising model, the magnetization is a solution to this equation, which has a name. So it's called the Burgers. This is called the Burgers equation. The Burgers equation, which is a prototype for describing nonlinear waves propagating in a viscous setting. So there is a diffusion term here, and then a nonlinear interaction here. And it's the simplest possible model that couples nonlinearity and viscosity and diffusion. So, in particular, so if we look at how n is defined in terms of the partition function, so is the derivative with respect to x of the log of Zn. So this is in the theory of the Burger's equation. This is what Burger's did in linearizing the equation. So realized that by applying this the Kolop transformation. Yeah, actually, I'm not sure if actually Burger's did it originally, but so this is called the Kolop transformation. So, and this is the transformation that takes the Burger's equation, transforms the Burger's equation into the heat equation. So, this is just a note in the literature. So, is yeah, no, there is of course 1 over n. Yes, yeah, is 1 over n, the derivative of the log. Yeah, I just combined the two steps together, yes. So Mn is 1 over n, the derivative of the log of z, and this is the transformation that allows to integrate the Burger's equation exactly by linearization, okay? So here we get to there in a different way by applying different arguments for the studying of the asymptotic limit. So, but here, in the limit where n tends to infinity, things are different because the equation in the limit where n tends to infinity, at least as long as this derivative stays finite, the second derivative stays finite, so at least naively, we can look at the problem, at least in first instance, by ignoring this term, and we get something meaningful at the leading order. Okay? In other ways, we say, okay, let's take an expansion of m in powers of 1 over n, and then at the leading order, so we see what we get. So Mn is going to 0. Why? No, not in general, no. Why it should go in general? The magnetization. We'll see in a moment. Yeah, we will see in a moment. So if we say, at least, you know, from the point of view of the perturbation theory, we expand M in, you know, in as a power series in 1 over, asymptotic series in 1 over n, and we look at the leading order. So in first instance, you know, as long as this diffusion term is bounded, 1 over n we can neglect it, and then at the leading order we get the derivative of m with respect to t equal to 2m, the derivative of m with respect to x. And the initial condition is the same because there is no dependence on n. This is the hyperbolic tangent of x. So at the leading order, as long as this assumption is accurate, so the equation is the Hopf equation, or Riemann-Hopf equation. So the Riemann-Hopf equation with this initial condition. So the initial condition means that, so the interaction, the external field is x is the external field, the constant external field, and t is the time in this equation. So we get this, we have this evolutionary equation. T is the coupling or the temperature. So remember that T is proportional to the coupling, the coupling constant between the spins divided by the temperature. So you can increase T by either decreasing the temperature, lowering the temperature of the magnet, or decreasing J, the coupling constant. So these two things are completely equivalent. And the initial condition is the hyperbolic tangent, so it looks like this. So this is 1, this is -1. So when the external field is 0, it is 0, and when it is non-zero, of course, it is driven by the external field. And then the interesting, one of the nice things of this way of looking at this is that the magnetization depends on X and T, depends on the external field and this ratio between pairing, coupling constant, and temperature. And then the magnetization behaves like a Riemann, a nonlinear wave, evolving in this space of the thermodynamic parameters. When one of the variables, T, plays the role of the time, and X plays the role, is interpreted as the space. So, and the evolution and the magnetization changes in the space of parameters evolves as a nonlinear wave of this solution to the Riemann-Hopf equation. So how do we solve this equation? By using the method of the characteristics. Okay, so this is solved exactly. So I will just do it. So you introduce the characteristic line, say X, a characteristic line in R squared, and such that dx by dt is equal to -2 times m, and then it follows that if m is a solution to the equation, the total derivative of m is dm by dt minus 2m dm by dx, and this is equal to 0, right? So the derivative of m with respect to t is 0, so m is constant along this characteristic line, and then this can be integrated straight away. This is x equal to minus 2m times x plus a constant which we parameterize using m itself. So m itself. So the solution m is given implicitly by this formula. Okay, 2m is the phase speed, and the 2m is. So this equation tells me that if I pick a point here on the initial profile, a point on the right-hand side will travel to the left with a speed that is proportional to the height. So this means that higher points travel faster than lower points. And on this other side, due to the symmetry, so it happens the same, but from the other side. So this means that at a later time, if I decrease the temperature, so I increase T, so the profile of the wave becomes steeper and steeper until you reach a point where the derivative at the origin here, dm by dx, diverges. So this is the point of gradient catastrophe. When the derivative is divergent, clearly this means that in the original equation, it's no longer true that I can neglect the correction. So I have to go back to the original equation to describe physically in the model what happens at a later time. Of course, the solution to this equation can be the roots of that equation can be calculated beyond the critical point where you have the gradient catastrophe, and then you will get a profile, a multi-valued profile like this, which means that the model develops more than one stationary point for the free energy. So this value of the magnetization is admissible, this value is admissible, and this value is admissible. But 0, which was the only solution at the initial time, and until you reach the gradient catastrophe, 0 was the stable solution. Beyond the critical point, this becomes unstable, and either this or this is the stable solution. So, for example, if you remember from the high school, the pressure volume diagram in the van der Waals equation of state below the critical temperature. So the van der Waals isothermal curve looks like this. There is this oscillation, and this is exactly this oscillation. And Maxwell, in a paper in Nature, where he cited the PhD thesis of van der Waals himself, so he devised the famous equal area rule to place the jump between this point and this point. So Maxwell proved that essentially the condition for the phase transition corresponds to the request, the chemical potential here and the chemical potential here are the same, and this corresponds to cutting the van der Waals solution in two lobes of equal area. Here, so beyond the critical point, you have this multivalid solution, and you can recover a weak solution to the Burgers equation by placing a jump right in the middle, which is such that this lobe and this lobe have the same area. This is equivalent to the Maxwell rule. So we can recover the weak solution to the Burgers equation using the Maxwell rule, but actually now we can do the same by calculating proper asymptotics of the Burgers equation, of the Poisson formula for the Burgers equation. So this can be done also rigorously. You take the Poisson formula for the Burgers equation, and so the solution of the Burgers equation in terms of the Poisson formula, and you do the Laplace theorem at the leading order, and you construct analytically this jump. So one comment. So in this formula here, this function f, in general, this for any choice of the function f, this is a solution. This is a solution to the Riemann-Hopf equation. In our case, we need to match this with the initial condition. So the choice of f is induced by the initial condition. So for t equal to 0, this is equal to x is equal to f m of x0. Okay, but m, the initial m is the hyperbolic tangent of x. So this means that f of m is the inverse, the arctangent, the hyperbolic arctangent of x. Okay, so the actual solution is given by this equation, where f is arctangent of m. Okay, where f of m is the hyperbolic arctangent of m. And this is this kind of give us the last consistency check with the with what we know in the literature. So let me write the the solution to the Riemann-Hopf equation in our case. So this is x plus 2mt is equal to the hyperbolic arctangent of m. And then we can just rewrite it, reshuffle things a little bit. M can be written as the hyperbolic tangent of x plus 2m times t. If we go back to the original notation, so m is the hyperbolic tangent of beta j divided by 2 times m plus beta h. So, which is in the theory of the mean field spin, the mean field easy model. This is called the is the self-consistency equation. So the self-consistency equation, so the equation of state for the mean field easing model, is a particular solution, is obtained as a particular solution of the Burger's equation at the leading order in the limit where n tends to infinity. So the equations of state are seen as particular solutions to some partial differential equations. And just a note, this self-consistency equation is the equation of state you obtain when you do the mean field approximation. So if you say that you replace the Hamiltonian with a Hamiltonian where each spin does not interact with individual spin, but with the average field, you derive in this classical book, in standard books, you derive this equation in that way. So here we derive it with no combinatorics essentially, but using the differential identity on the partition function and performing a large n limit. So I don't have time to do it explicitly here, but if you want to look at the rigorous leading order, so calculate the position of the jump. So calculate the position of the jump and what happens at the later time. So you can do this by performing by applying the Laplace formula, the Laplace theorem for the asymptotics of the Poisson formula in an integral form. So for an integral, no? in the large n limit. So in this case, this position, the solution beyond the critical point becomes a shock. You have a discontinuity, so you have a weak solution to the Riemann-Hopf equation, and the speed of the shock is given by the average. So the speed of the shock is given by the average between the value at these 2 points. But in this case, the average is 0, and the shock is just still at the origin. Okay, so what happens is that the shock doesn't move in this configuration because you have asymmetric initial condition. Okay. So if there are no questions, I can move on to the case Q equal to 3, which is requires a bit more attention. So so this example gives us a sort of consistency check, that what we obtained, of course, we obtained the classical results, and also we have an interpretation of these results in terms of the theory of PDEs. But the Riemann-Hopf equation is omnipresent in this business because it always arises as a limit in some regime. Of course, there is always a reduction that takes you to the Riemann-Hopf equation. So in the case where you have 3 possible choices of the spin, and choose sigma I to be equal. Again, for convenience, I choose sigma I to be 3 symmetric values, so -1, 0, 0, and 1. So again, we need to calculate explicitly the delta, which is 3/2 sigma I squared, sigma j squared plus 1/2 sigma I, sigma j minus sigma 1 squared, sigma I squared plus sigma j squared plus 1. Okay, so if we do the calculation for the delta, we get this this thing for this choice of the A's. Okay, so and then we can write the Hamiltonian. We see now we define the magnetization is still relevant. So mu1 is defined as before. So the sigma, the sum of the average, the arithmetic mean of sigma i's. But you see here, if it's not enough, the magnetization itself is not enough, right? So because we got these squares, okay, we got this quartic term and the squares. So what we need to define is the second momentum. So mu1 is the first momentum. So the second momentum is sigma I squared divided the average of the second momentum. So in terms of these two variables, so we have h, we can write an algebraic expression of h in this form, minus nj divided by 2, and then we get mu1 squared plus, so mu1 squared divided by 2 plus 3 over 2 mu2 squared minus 2 times mu2 minus n, and then we get the external interaction. So h1 mu1 plus h2 mu2. So we see this version of this variation of the Potts model contains this extra external field, which is not natural physically, because why you have an external field that couples not the direct with the direction of the spin, but its orientation, right? So whether it is 1, you have a contribution, -1, you get the same contribution. If it is 0, you have a different contribution. But actually, just as a side note, because this is how actually it was natural for me to suggest that, because before looking at this, I had looked at the models for liquid crystals, and in liquid crystals, you have the couplings that depend. Liquid crystals can be viewed as magnetic rods, where the coupling depends on their orientation, but the direction doesn't matter. So in liquid crystals, it's very natural to consider interactions like this. So then it was natural to incorporate this additional term in the Hamiltonian. But we will see that this is crucial in order to get the equation of state for the Potts model, which were not known because you need this extra term to close your relations. So we will. I'll describe briefly what we obtain in this case. So in this case, the partition function will be described in a. We will perform the similar. We will introduce the similar notation. So define x as beta h1, but then I will have another field, another variable y, which is beta h2, and then I will have t, which is beta j as before, divided by 2. So I've got now not 2, but 3 variables, x, y, and t. The external fields and the internal coupling. And then if we use this notation, mu1 and mu2 and these variables, so by direct differentiation of the partition function, we can derive a PDE for the partition function, which unsurprisingly will be the heat equation up to a transformation, the heat equation in 2 dimensions. Okay, so so what is so the equation becomes. So the price we pay when we add more degrees of freedom to the spins is that we have to increase the number of independent variables in our PD, which in general might be a big problem, because when you increase the number of independent variables, for example, in integrability, we know that beyond 2 plus 1 dimensional, apart from some particular situations, there is no integrability in the sense of lux, for example, in higher dimensions. So there is this is not like generally a minor thing. In this case, it's fine. It will be fine. So derivative of z by dt plus 2 times dz by dy equal to 1 over n, and then we got the diffusion term 1 over 2, the second derivative of Zn with respect to x, plus 3 over 2 d squared Zn dy squared, right? And locally, so when we look at the initial condition, so the initial condition can be still calculated. We have more variables, but since t is equal to 0, there is no, in the Hamiltonian, t is equal to 0 is like putting j is equal to 0. The partition function is still linear in mu1 and mu2, and we can follow the same trick, right, and calculate explicitly the initial condition, 1 plus 2 exponential of y, hyperbolic cosine of x to the power n. Okay, so this is the initial condition as set by this this linear expression in terms of mu1, the new variables mu1 and mu2. So now, if we want to do the large n limit, so large n limit, we need to essentially, I define the free energy as I did before, 1 over n, the log of Zn, and then I define f as the limit where n tends to infinity, or Fn, okay? And then I rewrite this equation in the limit where in the free energy, and then we just as we did before, as long as this is allowed, we ignore the 1 over n correction. Okay, so what do we get? We get the equation for f, so df by dt plus 2 times df by dy minus 1 over 2 df by dx squared, okay, minus 3 over 2 df by dy squared equal to 0. Okay, and the initial condition is x, y, 0 is just the log of 1 plus 2 times exponential of y, the hyperbolic cosine of x. So if I haven't forgotten anything, plus 2, yeah, minus. So essentially, it's the symbol of this differential operator, right? So this the classical limit. So, and how do we solve now this? So now we use the expectation value mu1, m1 is the expectation value of mu1, and then we need to work also with the expectation value of the second moment, mu2, and we write down the equations for mu m1 and m2 by differentiating this first with respect to x and then with respect to y, and then we get the equations. So the derivative of m1 with respect to t equal to, we get a nice conservation law, okay, m1 squared plus 3 over 2 m2 squared minus 2m2 by x, and then dm2 by dt, and then we get the same expression differentiated with respect to y. But also we need to consider the fact that mu1, m1, and m2, let me write them here. So m1 is the derivative of f1 with respect to x, and m2 is the f with respect to x, derivative of f with respect to y. So similarly, as before, m1 is the derivative of f with respect to x, and m2 is the derivative of f with respect to y. So these two equations for m1 and m2 need also the consistency. So the derivative of m1 with respect to y must be equal to the derivative of m2 with respect to x. So we get these two equations and this equation here. They need to go together. All right? So, and this is fundamental because now we can integrate these two equations using the method of the characteristics again. Okay, just slightly tweaked with respect to the previous example. Okay, but now it's apart from the details, it should be quite intuitive what we are doing. First of all, we use this closure relation, so this relation to write the two equations in a diagonal form. So what I want to do, I want to write the first equation where the derivative, I only see the derivative of m1. In the second equation where I only have derivative of m2. So the derivative of m2 with respect to x will become derivative of m1 with respect to y. So this is dm1 by dt equal to m1, the derivative of m1 with respect to x, plus 3m2 minus 2, derivative of m1 with respect to y. And similarly, derivative of m2 with respect to x equal to m1, the derivative of m2 with respect to x, plus 3m2 minus 2, completely symmetric, derivative of m2 with respect to y. Okay? So, and then we can define now the characteristic lines dx by dt equal to m1, and then dy by, the derivative, dy by dt equal to minus 3 m2 minus 2. And this implies that the total derivative of m1, so along the characteristic lines defined by these equations. Now I'm looking at characteristic lines in 3D, and so dm1, the total derivative of m1 along the characteristic is 0, and the derivative of m2 along the characteristic lines is 0. So this means that I can integrate the equations for the characteristic lines, and then I just write down the equations we get. So x plus m1 times t minus 1 over 2 log of m1 plus m2 divided by m2 minus m1 equal to 0, and then we get y plus 3 m2 minus 2 times t minus 1 over 2 log of m2 squared minus m1 squared divided by 4 times m2 minus 1 squared divided by 0. Okay? So I integrated these two characteristic lines, and then I put here, not in general, you would have here some arbitrary functions of M1 and M2, because any constant along the characteristic line. So these values here are chosen, I worked it out, of course I worked it out, in such a way that the initial conditions are worked out from the initial conditions. So these two functions here are such that when you restrict these equations to t equal to 0, you recover the initial conditions. Okay, so the initial conditions would be d by dx, the log of 1 plus 2 exponential of y, hyperbolic cosine of x, and then for m2 you get the similar. So d by dy of the same thing, right? So these functions here are chosen in such a way that when you take t equal to 0, you recover this initial condition. Okay, there is some inversion of, but nothing deep. Okay, so so these two equations are the equations of state for this version of this slightly generalized version of the Potts model. Okay, and somehow, you know, the fact that you need this extra momentum, this is essential in order to derive these equations, because we can close the differential identity and then do the limit and then integrate. So once we have that, we can recover the standard version of the model by taking just y equal to 0, or just as often happens, people look at the case where there is no external field. You just look at the spontaneous breaking, symmetry breaking with no external fields. So you can choose x and y equal to 0, and you will recover exactly the same phenomenology. But these equations of state provides like a richer picture, which I will quickly describe, because we have phase transitions also with external fields. And this is a major difference from the Q-revised, the Ising model, in the case of Q equal to 2, where the only phase transition occurs at 0 external field, at the origin. So in this case, in the x and y plane, we have phase transitions criticality also away from the 0 external field, the case of 0 external fields. So what the So in both cases, at the leading order in the thermodynamic limit, the equations of state are obtained as solutions to quasi-linear hydrodynamic type systems. In the previous case, 1 plus 1 dimensional. In this case, is 2 plus 1 dimensional. So somehow the thermodynamic limit is underpinned by the theory of quasi-linear hydrodynamic type systems. And the singularity of these nonlinear waves solutions of these hydrodynamic type systems correspond to the occurrence of phase transitions in the actual thermodynamic system. So we can describe the phase transitions as shock wave singularities in hydrodynamic type systems. And the corrections are essentially the regularization procedure for those in those phase transitions. So probably the last thing, given that my time is almost finished, I probably make a comment on because we derived the equations for M1 and M2. What about the free energy, F? right? So the free energy, so let's remember, so the free energy, let me use this notation for the partial derivative. So ft was equal to fx squared divided by 2 plus 3 over 2 fy squared minus 2f fy, right? Which, given the definitions, so this is m1 squared divided by 2 plus 3 over 2 m2 squared minus 2m2. So now let's take the characteristic lines. So x of t, y t, and t, and then let's look at what happens to f when we differentiate along the characteristic lines. Okay, we calculate the total derivative of f as a function of xt, yt, and t. So what is this? So this is the partial derivative of f with respect to x times x dot, the derivative of x with respect to t, the partial derivative of f with respect to y dot, plus the partial derivative of f with respect to t, right? So, but now we can use the actual relations. So, what is x dot? Is the derivative of x with respect to t is equal to minus m1. So, this is minus fx times m1. Is it was it at minus or let me see if just no, I'm doing something different here. So I'm doing something different. So I want to keep x dot, and then I remind myself that the partial derivative of f with respect to m is with respect to x is equal to m1, and this is m2, right? So I write this as m1 x dot plus m2 y dot, and then I use the equation, the partial differential equation for f, and I use the right hand side instead of this term. So this is plus m1 squared divided by 2 plus 3 over 2 m2 squared minus 2 m2, right? So, and now since I'm working along the characteristics and I want to calculate f, m1 and m2 are constant, and I can integrate this right away. So I can integrate, this gives me f equal to m1 times x plus m2 times y plus all this term m1 squared divided by 2 plus 3 over 2 m2 squared minus 2 m2 times t plus an arbitrary function of m1 and m2, okay, which needs to be chosen to match the initial condition. So this gives me an expression of the explicit expression of the partition function in terms of m1, m2, and x and y. And the nice thing is that the derivative, if I calculate the partial derivative of m1 with respect to of f with respect to m1 equal to 0 and df m2 equal to 0, okay? So these are exactly the equations of state. This corresponds to the equation of state. So we recover the intuition that in terms of the m1 and m2 are the order parameters. In terms of the order parameters, the critical points of the free energy as a function of the order parameters provide us the equations of state. So provided that the function f is chosen to match the initial condition. Okay, so I can write the expression. I just so yeah, probably yeah. I'll write the expression in a moment because I can write a nicer expression in better variables in a moment. Okay, so let me just confirm the point. So I could use the equation for f and the equation in the characteristic equations to derive the explicit expression of f in terms of m1, m2, x, and y. And then the critical points of f with respect to the order parameters give us exactly the equations of state. So we can write this expression in terms of the order parameters m1 and in m2 in a more kind of in a more symmetric way. Okay, and this is the last thing I'll probably. So yeah, I write this expression and probably I can sketch the graph of the phase diagram just to give an idea of what these equations provide us. So this is just a small technical bit. If I replace f with f minus t, I redefine the free energies by shifting t. I can write this the solution in a more symmetric way by introducing these variables: p1 equal to m1 plus m2 divided by 2, and p2 equal to m2 minus m1 divided by 2, and p3 equal to 1 minus m2, right? So, because m1 is the first momentum, m2 is the second moment, there is no symmetry there. But p1, p2, and p3, they are not all independent, because the sum of pi, where I tends to runs from 1 to 3, is equal to 1. And then you see that P1, P2, and P3 add to 1. They are positive by definition. And they correspond to the probability that macroscopically the system lives in a state where all the sigmas are equal to 1, all the sigma are equal to -1, and all the sigma are equal to 0. So, for example, if all the sigmas are equal to 1, so M1 is 1, M2, the second moment, is also 1, P1 is equal to 1. But P2 will be equal to 0, 1 minus 1 divided by 2, M2 is 0, P3 is equal to 0. So if all the moments are equal to 0, so all the spins are equal to 0, this means that both M1 and M2 are equal to 0. So this is 0, and P3 corresponds to the probability that the system is corresponds to the configuration of all zeros. So P1 and P2 and P3 can be read as probabilities of finding the system in one of these three states. Okay, in general, M1 and M2 will be whatever expectation value. So in terms of these variables, the function f becomes I just keep m1 x plus m2 y as the first term, but then the middle term, the term that corresponds to the multiplies t, is pk squared times t, and then the function f, this function f that is matches the initial condition, is the sum where k runs from 1 to 3 of pk, the log of pk. So Of course, I can express this in terms of P1 and P2, but just for shortness, I left them like this. So this term, the term that generates the characteristic speed is this, the sum of pk squared, and then minus this term that corresponds to the initial condition is the entropy. Is what the expression of the entropy of the system. This corresponds exactly with the entropic contribution. So, and we derive this by solving a system of hydrodynamic type using the method of the characteristics. At least under the assumption, as long as we are away from the gradient catastrophes, from the singularity. So, what does the solution look like? So this essentially what we need to do is to look at these equations, the equations of state as a map of the plane. So where M1 and M2, okay, are mapped into df by M1, the derivative of f by M2. So the equations of state can be viewed as a map of the plane, and then the critical points lie where this map has a singularity. So we can use the classification of singularities of the maps of the plane to identify the critical points. So Whitney in the 1950s has classified this completely, and in particular for a map of the plane, there are only two types of singularities. So the first one is given by the condition where the Jacobian of the map is equal to 0. Okay, so let me write it as d psi by dm1, d psi by so psi 1 by m2, and d psi 2 by m1, and d psi 2 by m2, where psi 1 is df by dm1, and psi 2 is df by m2, right? So the condition, the first singularity, type of singularity, is where j is equal to 0, and this is called a fold singularity. A fold singularity. And then we have the second type of singularity is a cusp singularity that corresponds to the subvariety that is tangential, such that the gradient of the map is tangential to the fold. Okay, so this variety is called the general fold. And then the cusp corresponds to the condition where d psi I by dm2 dj by dm1 minus d psi I by m1 dj by m2 is equal to 0, with I equal to 1, either I equal to 1 or 2. So this condition corresponds to the condition where the gradient of the map is tangential to the general fold. Okay, so this d psi by m2 minus d psi I by minus 1 are the component of the orthogonal vector to the gradient. So we request that the general fold is and the gradient are parallel, right? And these are the only singularity you can have as far as the maps of the planes are concerned. And then you can calculate using those equations. I don't provide the details here, but you can calculate these conditions by explicitly using the expressions we derived. And for example, if you look at the in the plane M1, M2, the singularity, the cusp singularity lie on two straight lines. So you have two straight lines passing through this point, and then you have, so there are, when you calculate these conditions, you get this condition factorized, and you get two linear factors, so two straight lines, and then you go a quartic. So the quartic, if you plot the graph of the quartic, it would be something like this, encircling the intersection between the two straight lines. So the singular sector for this system is given by the union of these two lines and plus a quartic. So what happens to the graph of M1 or M2 when you cross these singularities? So what happens if you look at M1, for example? So M1 is something like this. So M1 is something like this. And then when you reach, imagine that you choose a particular value of x, a particular value, you fix t. Imagine you fix t and you fix y, and you are, say, you are somewhere here. Let me see, say here. So what you will see is that when you cross the one of these lines, what you see is that you will see a gradient catastrophe. Okay, so you will see a gradient catastrophe that is placed symmetrically on the two sides. Okay, so and then there'll be more catastrophes when you move further. So, for example, you can map this from M1 and M2 to X and Y, and the graph will look at the two lines. So the linear variety will map into this. This is the origin, right? So we'll map in these two lines, and then the quartic maps into this. Still a quartic. You know, it's a quartic in M1 and M2, but then you have a transformation with logs that kind of change the things. So, and then, for example, you know, if you look at M1 in this case, you will see that, you know, you will have M1 something like this. And then when you reach these points, you will have a gradient catastrophe, right? And then they will, you will have a weak solution, and they will collide in right in the center. This would be the graph of M1. Okay, so the cusp corresponds to the condition. So you will see the gradient catastrophe in correspondence of the cusps. Okay, so the general fold corresponds to the condition where you have a vertical tangent. So when the graph of M1 becomes, you know, multivalued like this, these 2 points are points where J is equal to 0, okay, but the so-called transversality condition, the non-transversality condition is not verified. So this is the general fold, and when you have the gradient catastrophe, this is the cusp, where you have J, the Jacobian is 0, but the non-transversality condition is also verified. Okay, so this gives us like a complete picture of the phase transition, of how to describe the phase transition in this asymptotic limit, with some assumptions, because we are not looking at the diffusing, the effect of the diffusion, but the effect of the diffusion will regularize this, will prevent this multivaluedness to occur, right? And then it will produce in the limit a jump.